So in this video, I'm going to go over what you need to know in terms of graphs for exponents and logarithms in terms of the Cambridge Additional Maths IGCSE from 2020 onwards. So the first graph we have here is of e to the power of x, and as you can see, it crosses the y-axis at 1, and it has an asymptote at y equals 0 here. Next, we have a graph of the natural log of x, which crosses the x-axis at equals 1, and it has an asymptote at x equals 0 here. So when we put the two graphs together on one graph, I've also added in here y equals x. We find out that they're actually just the inverse of each other, as we can see from this bit here. These are also some of the properties of the graphs for each function. As you can see, this one, the domain is that of real numbers, but a domain for a log graph, x has to be bigger than 0. And this is reversed in the range here. See, for an exponent graph, there's going to be a horizontal asymptote, but on a log graph, there's going to be a vertical one. Also need to know graphs in the form of k times e to the power of nx plus a, where k, n, and a are all integers. So I put these graphs down the side to kind of help you visualize which kind of one does what, but I'll explain as well. So a, the plus a we have at the back here, represents a vertical translation. So that's if it's moved up or down or not. The n here in the exponent here represents a horizontal stretch by factor of 1 over n. The k at the front here is a vertical stretch instead of a horizontal stretch. So when k is bigger than 1, it's being stretched, but the graph will be compressed if k is in between 0 and 1. Some other properties, so if we take this one down here, for instance, this graph here, when there is a minus in front of the k, that means that it's going to be flipped in the x-axis. So we can see here when k is minus 1, it goes down, whereas when k is positive, it goes up. However, if we change n, so I've left k as 1 here. If we put n as minus 1, this one up here as minus 1, we can see that the graph's flipped in the y-axis. And here, when k is minus 1 and n equals minus 1, we can see it's flipped in the y-axis and the x-axis. Also need to know how to plot graphs in the form k times the natural log of ax plus b, where k, a, and b are all integers. So again, I've done the same thing. I put some graphs here to help you visualize what each one does, as well as this box here explaining kind of the transformations that can happen. B is going to account for a horizontal translation, aka if it's moved left or if it's moved right. Our k here is going to be a vertical stretch or compression, depending on if it's bigger or less than 1. And our ax over here is going to be a horizontal compression or stretch, depending if it's bigger than 1 or less than 1. And here we have a quick example of a question you might be asked in terms of graphs of exponents and logarithms, which asks you to consider the function f of x equals log of base 2 x minus 1 close bracket plus 1. And the first thing it wants to do is to find the domain and range of the function. Quick recap, I'm sure you know, but the domain counts for the x values that the graph takes up and might stretch you, and then the range is the y values. So whatever inside a log base 2 needs to be bigger than 0, so we can make what's inside the log 2, which is the x minus 1, bigger than 0 here in an inequality, and then we can move the 1 over to the other side to get x needs to be bigger than 1. So this is going to account for our domain, and because there's no real restrictions on the y here, the y is just going to be within the set of real numbers, and that gives us our domain and range. Then it wants us to find any asymptotes or axis intercepts. So we know from our domain here that x is always going to have to be bigger than 1. So we know that 1 straight away is going to be our vertical asymptote as it is an x value. Y is just within the set of real numbers, so there's going to be no horizontal asymptote for this graph. And we said that x needs to be bigger than 1, so if we looked at that in a graph, we were going to see that it's not going to cross the y-axis, and therefore there is no y-intercept, but there is going to be an x-intercept because y is within the set of real numbers. So to do this, we're just going to find where the graph crosses the x-axis, which is when y equals 0. Gonna equate our equation here, our function, to be 0, and then as we can see here, we've just moved the minus 1 to the other side to get log base 2 x minus 1 equal to minus 1. We can then use our rules of logarithms to work out that log of 2 x minus 1 equals minus 1. We can flip that around so that it becomes x minus 1 equals 2 to the power of minus 1. And then we can solve this to get x equals 1.5. So this is our x-intercept. So from this point, sketching the graph, which is the next thing they want us to do, should be quite easy. We worked out our x-intercept, we know our asymptote, so we know that it's going to tend towards x is equal to 1, but it's never going to reach it, so we know this is where we should start drawing our graphs from. You can put in some random values of x or y to work out points and just plot the graph, basically. The last part of this question is they want us to find the inverse of the graph. And we can do this by switching around the x's and the y's in our equation function here, and then solving for y. So first of all, we're going to take this plus 1 on this side, and we're going to take it over to the other side to give x minus 1 equals log 2 y minus 1. Using our laws of exponents, we're going to get rid of this log of 2 here, and instead that's going to be the 2 from here is going to be to the power of x minus 1, so that gives us y minus 1 equals 2 to the power of x minus 1. We're then going to move the 1 back onto the other side so that we solve for y. And once we do this, we find that the inverse of our function is 2 to the power of x minus 1 plus 1.